morning, students. Now we have magnetic field due to a toroid. You know about the toroid. Toroid is a ring-shaped solenoid. The cross-sectional view of toroid is like this. The permanent lines represent toroid and cross and dot represent that current is coming out of plane of paper and cross is current is going into plane of paper. So the current in the turns of toroid passes like this. Okay. Now there are 3 Amperian loops in dotted lines 1, 2 and 3. Okay, on the basis of radius. Depend on radius, there are 3 regions. One is in the interior of toroid, one is inside the toroid, and one is outside the toroid. Okay. For first, in the interior of toroid, radius R1. The radius of Amperian loop is R1. Inside the toroid, radius is R, and outside the toroid, radius is R2. Okay. Now consider a toroid having small n turns per unit length. Okay. As we have 3 regions, so 3 cases are there. The case first is magnetic field in open space in the interior of toroid. Okay. As this is the application of Ampere Circuit Law. So according to Ampere's Circuit Law, we have the line integral of B into dl is equal to mu naught I. Okay, but this Amperian loop with radius R1 does not encloses any current. No current passes through this Amperian loop. Okay, there is no current enclosed by Amperian loop in case of the interior of toroid. So I is equal to 0. Okay, then the line integral of B into dl is equal to mu naught into 0. So we get the line integral of B into dl is equal to 0, as we know that in case of circular Amperian loop, B and dl both are in same direction. So we take cos 0 in dot product. Okay, cos 0 is 1. So we get B line integral of dl. B is taken out because the value of magnetic field is constant. B line integral dl is equal to 0. By this we get B into 2 pi r1. The line integral of dl around this Amperian loop is the circumference, that is 2 pi r1 is equal to 0. From this we get magnetic field B equal to 0. Okay, so the magnetic field in open space in the interior of toroid is 0. Okay, get it? Yes. Case second, magnetic field in open space in the exterior of toroid. This is exterior of toroid, this Amperian loop with radius R2. For this Amperian loop, current passes twice. In this case, current passes the loop twice. This and this both encloses by the loop. Okay, one is going into plane of paper by cross, we represent this. Another coming out of plane of paper, that is represented by dot. So the current entering the loop is equal to the current leaving the loop. So net current is equal to 0. Okay, once again, the net current in case of open space in the exterior of toroid is 0. Then, according to Ampere's circuit law, B into dl line integral is equal to mu naught I. But the current is 0, so B dl cos 0, because B and dl are in same direction, equal to mu naught into 0. Thus, we get B line integral of dl is equal to 0. The line integral of dl around the Amperian loop is equal to 2 pi r2. So, B into 2 pi r2 is equal to 0, and by this, once again, we get magnetic field is equal to 0. So, magnetic field outside, magnetic field in the interior, both are 0. Now, the third case. Magnetic field inside the toroid. Magnetic field inside the toroid. For this, the current enclosed by Amperian loop, because only current passes one time. This is crossed. Okay, the cross represent the current entering into plane of paper, and this Amperian loop encloses only these crosses. Okay, so the enclosed current is equal to small n into 2 pi r. Small n is the number of turns per unit length, and 2 pi r. 2 pi r is the radius, so 2 pi r is the circumference and total distance of loop. Okay, so n into 2 pi r is the total number of turns, and I be the current in each turn. So n into 2 pi r into I is the current enclosed by Amperian loop, that is equal to 2 pi r into Ni. Equation number 1. Also, the line integral of B into dl, B and dl are in same direction, so we get B dl cos 0, then we get B line integral dl, and the line integral of dl in this case is 2 pi r. So, B into 2 pi r, the line integral of B into dl is equal to B into 2 pi r. Equation number 2. According to Ampere's Once again, according to Ampere's circuit law, the line integral of B into dl is equal to mu naught IE, enclosed current. Okay, so from equation 1 and 2, the B into dl is equal to B into 2 pi r is equal to mu naught. The value of IE is 2 pi r into Ni. So mu naught into 2 pi r into Ni. By 2 pi r cancel out. So we get B is equal to mu naught Ni. This is similar to solenoid because toroid is also a ring shaped solenoid. Okay, this can be written as B is equal to mu naught capital N I upon 2 pi r, where capital N is the total number of turns, that is small n is equal to capital N upon 2 pi r. Okay, this is the required expression of magnetic field in case of toroid. Okay, one new topic, force between two parallel currents. Okay, for this we have this diagram. In this diagram, consider two long parallel wires 1 and 2, wire 1 and wire 2, separated by a distance small d, carrying currents I1 and I2. Wire 1 carry current I1 and wire 2 carry current I2 respectively. Okay. Now these diagrams are the helping diagrams. Okay. As you have Fleming left hand rule, if the current and magnetic field is given to you, then you can find the direction of force. Okay, so with the help of these diagrams, the direction of F1 is towards wire 2 and the direction of F2 is towards wire 1. Okay, as you can see, this represent the current, this represent magnetic field, then this represent force. So in this, magnetic field is out of plane of paper, current is upward, so the force is towards wire 2. Okay, similarly we can give the direction of F2. Now the wire 1 produce a magnetic field B1. The wire 1 produce a magnetic field B1 at all points along the wire 2. It means the wire 2 is placed in the magnetic field of wire 1, and similarly the wire 1 is placed in the magnetic field of wire 2. Okay, so B1 is equal to mu naught I1 upon 2 pi t, because the magnetic field due to an infinitely long straight wire is mu naught I upon 2 pi r. So we have mu naught I1 upon 2 pi d. Equation number 1. Due to this force, the wire 2 experiences, once again, due to this magnetic field, due to this magnetic field, the wire 2 experiences a side wave force F2, this one, due to magnetic field B1. The wire 2 experiences a side wave force F2 due to magnetic field B1, that is, we have the formula IBL. So F2 is equal to current is for conductor or wire 2, that is I2, magnetic field due to I1 means wire 1, because the wire 2 is placed in the magnetic field of wire 1. So B1 and the length is L. So we have F2 is equal to I2 B1 into L. Put the value of B1, I2 into mu naught I1 upon 2 pi d into L. Rearranging this, we get F2 is equal to mu naught I1 I2 upon 2 pi d into L. the direction of this force is directed towards wire 1. Okay. Similarly, we can find the force F1 on wire 1. Okay, that is mu naught I1 I2 upon 2 pi d into L. This force is directed towards wire 2. Okay, these are the forces between two parallel currents. Okay, the remaining portion of this heading, this topic will be in next video. Okay.